Beneath the vast underground expanse of Kaiping, situated in southeastern China, a colossal neutrino laboratory is nearing completion. Descending 700 meters below the verdant terrain, diligent construction crews are finalizing a 35-meter diameter spherical detector designed to scrutinize ethereal subatomic particles known as neutrinos with exceptional precision. According to Yue Heng, a physicist from the Chinese Academy of Sciences Institute of High Energy Physics in Beijing and the on-site manager of the $376 million Jiangmen Underground Neutrino Observatory, JUNO, if all proceeds as planned, JUNO will commence operations by the year's end. This initiative marks the forefront of several ambitious neutrino detection projects worldwide. Two others, one in Japan and the other in the United States, are slated to commence data collection in 2027 and 2031, respectively. The primary objective of JUNO is to assist researchers in determining which variety of neutrino possesses the greatest mass, a long-standing enigma in physics. This endeavor holds promise in unraveling the mystery surrounding the nature of neutrinos and the reasons behind their minuscule mass. To achieve this, JUNO researchers intend to analyze neutrinos emanating from two nuclear power facilities situated over 50 kilometers away. Additionally, they aim to investigate neutrinos originating from various sources, such as the sun, atmosphere, celestial explosions, and natural radioactive decay processes within Earth. On March 7, scientists at the observatory initiated the process of filling a scaled-down version of the detector with liquid scintillator, a blend of solvent and organic chemicals that emits light upon interaction with neutrinos. This miniature model, named OSIRIS, serves to ascertain the purity of the scintillator, crucial for resolving the mass-ordering conundrum. Distinguishing itself from other forthcoming detectors, JUNO adopts a distinctive approach. While Japan's Hypercameo Kande detector plans to utilize purified water and the deep underground neutrino experiment in the United States will rely on liquid argon, JUNO employs liquid scintillator. Moreover, while the latter experiments will focus on neutrinos from nearby particle accelerators, JUNO's attention will be on neutrinos from nuclear reactors and other cosmic sources. Similar to telescopes observing the cosmos across different wavelengths, the deployment of multiple neutrino detectors employing diverse methodologies offers a comprehensive understanding of neutrino properties and their cosmic significance. This multi-pronged approach ensures consistency and reliability in scientific findings. The liquid scintillator must exhibit minimal traces of uranium and thorium, radioactive elements that can interfere with neutrino detection. Consequently, meticulous testing of OSIRIS ensures the radio purity of the fluid before integration into the primary detector. Despite neutrinos being the most abundant massive particles in the universe, their detection remains challenging due to their weak interaction with matter. Nonetheless, elucidating their properties holds immense cosmological significance. The existence of three neutrino flavors, electron, muon, and tau, was established over 2 decades ago. Subsequent experiments revealed their capacity to transform from one flavor to another, indicative of their mass. However, determining the mass hierarchy remains elusive due to the need for larger, more sensitive detectors situated close to robust neutrino sources. Positioned beneath a granite hill, JUNO benefits from natural shielding against cosmic radiation, crucial for detecting faint neutrino signals. The ongoing construction involves submerging the acrylic sphere in 35,000 tons of high-purity water to further attenuate background radiation. Overcoming challenges, such as groundwater removal and radon control, has been pivotal in safeguarding JUNO's sensitivity. Situated between two nuclear power plants, JUNO capitalizes on a steady stream of electron antineutrinos emanating from these facilities, offering an ideal environment for precise measurements. Direct detection of neutrinos is unfeasible. Instead, physicists measure the energy of secondary particles generated when neutrinos interact with matter. JUNO's detection mechanism relies on inverse beta decay, wherein electron antineutrinos interact with protons, producing positrons and neutrons. These interactions generate characteristic flashes of light, discernible by photomultiplier tubes covering the detector. JUNO's scale, shielded environment, and proximity to nuclear power sources position it as one of the most sensitive neutrino detectors globally. This primes it to potentially unravel the mass hierarchy of neutrinos, marking a significant scientific achievement.